Okay, so our final talk of the day is by Grigori Karagulyan from the Institute of Mathematics in Armenia, who's going to talk about polynomial systems and Weyl multipliers. So,
there's a microphone, right? There's a microphone. I think I don't need that if it is okay. No. Okay, my talk is pure classical. I will talk some pure classical subject in theory of orthogonal series. I will start just a few. I will start with the general orthogonal series. Basically, the problems I will consider concern to the almost everybody convergence of general orthogonal and classical, some classical orthogonal series. So I will start with some couple of results and all classical and some results in general orthogonal system, general orthogonal series. Let us just remind to some two. There is also two definitions in the theory of orthogonal series. So we have orthonormal system of orthonormal functions. So we say the omega n is a Weyl multiplier for the system if you take any series with these coefficients. Any series with this coefficient converge almost everywhere. If the convergence holds for any rearrangement of the terms, then we say omega n is an unconditional convergent Weyl multiplier. So when omega is identically 1, then in this case it is said phi n is just convergence system. That means any coefficients you take in L2, all these series converge almost everywhere. And correspondingly, if the series converge almost everywhere after any rearrangement of the terms, then we say phi. In the case of general orthonormal systems, these results are well known and old and classical results. Menschov-Rademacher in 1923 proved that log square n is Weyl multiple for any orthonormal system. That means if you take coefficients satisfying to this condition, then the series converge almost everywhere. Also, Menschov proved that log square n is in this theorem is optimal. That is, if you take any other sequence or small o log square n, then he constructed an example of orthonormal system for which any omega n like this is not Weyl multiplier. As for the classical orthonormal system, it is well known. Almost many classical orthonormal systems are convergence system. Some of them are known some years ago, and for example, in 1966, Carlson proved the trigonometric system is a convergence system. That was not old-standing problem posed by Luzin. Then a few years later, Walsh for the same that was proved for the Walsh system by Billard using the Carlson method. So this is some very short review about in the case of general orthogonal systems. Let's pass to the case of. So in case of classical system, if there is no any rearrangement, all this classical system are good in some sense. So because in the context of these definitions are good because all are convergent system. But after rearrangement, they can be worse. So let us see what we have results. What results we have? Classical. So in 1927, Kolmogorov announced a result that that trigonometric system can be rearranged and get it is not unconditional convergence system. That means there is some rearrangement which is not a convergence system. Then the proof of this result will not given. Kolmogorov in 1960, Zagorsky gave a proof of this result, and Ulyanov, using the technique where Zagorsky proved that Hahn-Walsh system are also unconditional convergent, are not unconditional convergence system. Then, using this technique, Ulyanov and Alevsky a few years later proved that any complete orthonormal system can be rearranged to get non-convergent system. That is, any complete orthonormal system is not an unconditional convergent system. And here is completeness of the orthonormal system in the theorem is essential because there are many examples of orthonormal system which are unconditional convergence system. Simplest one is the Rademacher functions or any system of independent random variables. So the proof of Menshov theorem is based on the following inequality. This is the basic inequality in the proof, and in fact, this is the basic part of the proof. That means if you take any sum, the maximal sum, you take any orthonormal system of n functions, and the maximal function of the partial sums, then there is a estimate, logarithmic estimate, and log n is optimal, which follows for another lemma of Menshov of his paper. So in this estimate, also log n is optimal. There are two old problems in general orthogonal theory. The first is the following: that if it is possible, you have an orthonormal system, can you rearrange this orthonormal system to get a convergent system? This problem is still open, and another version of this problem, which is much stronger version of this problem, was post-Garcia. That is, if you take any finite orthonormal system, then is there a rearrangement such that you get such inequality? I just mentioned in the general case, in the theorem of Menshov, it was log n, so you have to rearrange the functions to get estimate without any dependent on the n. A standard argument, using standard argument, one can deduce the Kolmogorov conjecture from the Garcia conjecture. These two problems are still open, and there are some particular results concerning. First, Garcia proved that if you have a single series, then you can rearrange the series and get almost very convergent. But the general problem of Kolmogorov says you have to take a rearrangement independent of the coefficients, so which it will be common for the all L2 series. Then in 1988, Bourgain considered the problem of Garcia for the bounded orthonormal systems, but here you see the extra log n, which is better than, much more better than in the case of in the estimate of Menshov-Rademacher inequality, but the general question of Garcia says you should have here constant independent of n. Okay, so as any orthonormal system are not good in the sense of convergence system, you have to find some ways to find something good in the sense of almost every convergence system. One of these problems are the consideration of convergence in the partial sum subsequences, so partial sums of and the Menshov-Marcinkiewicz theorem is one of the such results. It is if you have a orthonormal system, then you can find a subsystem of natural numbers such that any series with L2 coefficients converge almost everywhere. And from this theorem, it immediately follows that any orthonormal system you have, you can find a subsequence of this orthonormal system, which is a convergence system. And also, Golmosh proved that in 80s, he proved that in fact you can take any orthonormal system contains an unconditional convergence system. That is here phi and k can be an unconditional convergence system. So a question whether in these theorems you can get some density of the sequences was arised in 80s. So first results was proved by Kashin, and he proved that there is a common some sequence of integers which is common for all orthonormal systems. So you can find you take any orthonormal system, you can find the subsequence of natural subsequence of this orthonormal system, which is convergence system, and nk are bounded by this nk. So that means you can so nk is important to say that nk doesn't depend on the orthonormal system. It is common for all orthonormal systems. That means you will have some density, certain density for the subsequence nk. And it turns out you can hear. So in the following result, you see nk can be can have such a rate of growth, and if you take bounded orthonormal system, then you can also find a subsequence which is unconditional convergence system and satisfy to this condition. Also, there is no density, any density property. So if you take any sequence, then you can not say the same for the unconditional convergence subsystem. So you can find any orthonormal system which is such that any sequence you take satisfying this is divergence system. Okay, let's. So whether this estimate is possible. So instead of lambda power k, can you write this estimate? It is an open problem. Later, How many minutes I have? 2?
There's a bit of a delay, so maybe 4. So you can go over by.
I think I have. I think I have 4 minutes.
I have 4 minutes.
Yeah.
And so let's now consider the properties of unconditional convergence properties of the classical orthonormal systems. In 1963, Ulyanov proved that this condition is necessary, sufficient for omega n, for Wn to be unconditional convergent multiplier for Haar system. And analogously, Georgian proved that Franklin for the same is true for the Franklin system. So as for the trigonometric and Walsh system, here is the problem was posed by Ulyanov in 1964. Those systems are quite different than Haar and Franklin system, and for the Walsh system, this in Bashkairov and Nakata in 1977 proved that this condition is necessary for Wn to be unconditional convergence multiplier for the Walsh system. For the trigonometric case, the problem was also for the Walsh case, the problem is open because the sufficient condition is not known. And as for the necessary condition, some partial results for Nakata, Galician, and we prove this condition again necessary for Wn to be unconditional convergence system. Now let us consider the sufficiency of this condition for the Weyl multiplier for Walsh and trigonometric system is open problem. Now let us consider some orthonormal system, and let consider some non-overlapping linear combinations, and suppose phi k is a orthonormal. So we get here orthonormal system, and for example, if jk is a single point sets, then you will get some rearrangement of this system. So what happens? So the general problem is thus characterized the Weyl multipliers of phi k when for any such kind of orthonormal system. So also some maximal inequality here is the so optimal constant here to find. These problems are connected to each other because the second one implies the first one, and so we consider this problem for the martingale difference systems and for the wavelet type systems. For the martingale difference systems, we proved that this constant is equivalent to square root log, and with the following corollary is that the Ulyanov's condition is necessarily sufficient for any polynomials, martingale difference polynomials, to be unconditional convergent system. The same we prove for the general wavelet type systems. This is the definition, standard definition of wavelet type systems, and we prove this constant is exactly as this read, and with the corresponding corollaries, that is this condition is necessary sufficient for all kind of non-overlapping polynomials with respect to wavelet type systems to be unconditional convergence system. Okay, I finished.
Thank you. Questions? Yes.
Maybe one comment. It makes sense to tell that till now there is no result about unconditional convergence to trigonometric series which differ trigonometric system from general orthogonal system. So it's very interesting problem. All in this area is very interesting.
Other questions? So I have a small question, which might just be my own ignorance. What is the Franklin system? What is the Franklin?
Franklin. It is not short to. Right. It is a spline. If you know,
Head functions which are
if you know
orthogonal.
spline systems,
Yeah.
it is a piecewise linear. This is the simplest spline system.
Oh, okay.
Orthonormal system.
You take
It
one
is
function
the
and
it is the first basis
I see.
constructed in C01. Orthogonal basis.
I see. Thank you. Any other questions? Okay, let's thank our speaker again.